Welcome to this comprehensive module on Kubernetes objects, a crucial component of modern DevOps practices. I'm excited to guide you through the fundamental building blocks of Kubernetes. In this module, we'll explore various Kubernetes objects, including pods, replica sets, deployments, services, config maps, secrets, and horizontal pod autoscalers. By the end of this session, you'll have a solid understanding of how these objects work together to create robust, scalable container orchestration solutions. Whether you're new to Kubernetes or looking to deepen your knowledge, this module will provide you with practical insights and hands-on examples that you can apply in your DevOps journey. Let's begin our exploration of Kubernetes objects. Let's begin our exploration of Kubernetes objects by examining their YAML definitions. In this section, we'll cover the fundamental building blocks of Kubernetes, starting with pods, the smallest deployable units. We'll learn how to define these objects using YAML, understand their structure, and explore the key components that make them work. This knowledge will form the foundation for managing containerized applications in Kubernetes. Let's dive into our first Kubernetes object, the pod. A pod is the smallest and most fundamental unit of deployment in Kubernetes. Think of it as the atomic unit of scheduling. You can't deploy containers directly. They must be wrapped in a pod. When working with pods, it's crucial to understand that they provide a shared execution environment for one or more containers. This means containers within the same pod share the same network namespace, which allows them to communicate via localhost, and they can also share storage volumes. Let's examine the YAML definition we see on the slide. Notice how we start with API version v1. This indicates we're using the core API group. The kind, pod specification, tells Kubernetes we're creating a pod object. Under metadata, we give our pod a name, which must be unique within the namespace. The spec section is where we define our containers. In this example, we're running an Nginx container exposed on port 80. This is a common pattern you'll see in web applications. One important note, while you can run multiple containers in a pod, it's generally better practice to keep pods focused on a single primary container unless you have a specific need for sidecar containers. A practical tip from the field. Remember that pods are ephemeral. They can be terminated and replaced at any time. Therefore, never write directly to a pod's file system unless you've attached persistent storage. Many developers learn this lesson the hard way when their application data disappear after a pod restart. The port specification we see here, container port 80, is important for network policies and service discovery, but it doesn't actually expose your pod to the cluster. That's what services are for, which we'll cover later in this module. Let's break down each component of the pod YAML specification in detail. Understanding these elements is crucial for effective Kubernetes deployment management. Starting with the API version, v1 refers to the core/v1 API group. This is one of the most stable and widely used API versions in Kubernetes. Different objects might require different API versions, and it's important to use the correct one for compatibility. The metadata section is more powerful than it might first appear. While we're only using the name field here, you can also add labels and annotations. Labels are key value pairs used for organizing and selecting objects, while annotations allow you to add non-identifying metadata for tools and libraries. In the spec section, we define our container configurations. While our example shows basic settings, you can also specify resource requests and limits, environment variables, volume mounts, and more. This is where you'll spend most of your time when fine-tuning your pod deployments. A critical aspect that's not immediately obvious from the YAML. Pods are scheduled as complete units. If you have multiple containers in a pod and one fails to start, the entire pod will be considered failed. This is why it's crucial to keep your pod definitions focused and not overload them with too many containers. Proper resource specifications and health checks are crucial for pod stability. While not shown in this basic example, You should always consider adding readiness and liveness probes to your pod specifications. Now let's explore replica sets, a crucial resource for maintaining high availability in Kubernetes. A replica set's primary purpose is to ensure that a specified number of pod replicas are running at any given time. This is fundamental to achieving both high availability and scalability in your applications. The key strength of replica sets lies in their self-healing capabilities. If a pod fails, is deleted, or is terminated, the replica set automatically creates a new pod to maintain the desired number of replicas. This automatic recovery mechanism is essential for maintaining service reliability in production environments. When it comes to scalability, replica sets provide a straightforward way to scale your application horizontally. You can increase or decrease the number of replicas based on demand, either manually or automatically through horizontal pod autoscaling, which we'll discuss later. However, it's important to note that while replica sets are powerful, they're often not used directly in modern Kubernetes deployments. Instead, they're typically managed by deployments, which provide additional features like rolling updates and rollbacks. Think of replica sets as the building blocks that deployments use to manage pod lifecycles. Working with large-scale applications, understanding replica sets are particularly important when debugging deployment issues or when you need fine-grained control over pod scheduling and scaling behaviors. They're also crucial for understanding how Kubernetes maintains desired state in your cluster. Let's examine the YAML definition of a replica set in detail. This configuration demonstrates the key components needed to maintain a specified number of pod replicas. The API version here is app/v1, which is different from the pod specification we saw earlier. This is because replica sets are part of the apps API group, which handles higher-level abstractions in Kubernetes. In the spec section, we define replicas, 3, indicating that we want 3 identical pods running at all times. The selector field is crucial. It determines which pods are managed by this replica set. The match labels section must match the labels defined in the pod template. The template section defines the pod specification that the replica set will use to create new pods. Notice how this template is similar to the pod YAML we discussed earlier, but it's nested within the replica set specification. A practical tip from production environments: always ensure your pod template includes appropriate labels that match the replica set's selector. The port specification, container port 80, in the template shows that each pod will run an Nginx container, exposing port 80. In a real-world scenario, you might also want to add resource limits, health checks, and environment variables to this template. When working with replica sets, remember that any changes to the pod template will not affect existing pods. They only apply to new pods created by the replica set. This is one reason why deployments are often preferred, as they handle updates more gracefully. Let's delve deeper into the components of a replica set specification, focusing on the crucial elements that make it work effectively in a Kubernetes environment. The app/v1 API version indicates that we're using a stable, production-ready API. This is important because Kubernetes APIs evolve, and using the right version ensures compatibility and access to desired features. The metadata section, while simple in our example, can be extended with labels and annotations for better organization and integration with other tools in your DevOps pipeline. For instance, you might add labels for environment tracking or annotations for deployment automation tools. The spec section is where the real power of replica sets becomes apparent. The replicas field determines how many identical pods should be maintained. While we've specified 3 here, this number can be adjusted based on your application's needs and resource availability. The selector is crucial for the replica set to identify which pods it should manage. The match labels field creates a relationship between the replica set and its pods. This label-based selection is a fundamental concept in Kubernetes that enables flexible and powerful pod management. In production environments, I've found that proper label management is critical. A common mistake is using overly generic labels that could cause multiple controllers to try managing the same pods. Always use specific, meaningful labels that clearly identify the application and its purpose. Continuing our deep dive into replica set specifications, let's focus on the template section, which defines the blueprint for creating new pods. The template section is essentially a pod specification embedded within the replica set. This template must include the labels specified in the selector section. The metadata within the template applies to every pod created by this replica set. The pod spec within the template defines the containers that will run in each pod. While our example shows a simple Nginx container, in real-world applications, you might include multiple containers, init containers, volumes, and various other configurations. A crucial point about the container specification: the image field should always specify a precise version rather than using latest. In production, using latest can lead to unexpected behavior and make rollbacks difficult. Instead, use specific version tags or image digests. The ports section in our example exposes port 80, but remember that this alone doesn't make the pod accessible from outside the cluster. You'll need a service object, which we'll cover later, to expose your application properly. I recommend adding resource requests and limits to your pod template, even though they're not shown in this basic example. This helps prevent resource contention and ensures proper scheduling of pods across your cluster nodes. Also, consider adding readiness and liveness probes to your container specification. These probes help Kubernetes determine if your application is healthy and ready to serve traffic, which is crucial for maintaining high availability. Let's discuss some critical considerations when working with replica sets in Kubernetes. These insights come from real-world experience and can help you avoid common pitfalls. First, it's crucial to understand that replica sets are immutable by design. This means that certain aspects of the replica set, once created, cannot be modified. For example, if you need to change the pod template, you'll need to create a new replica set. This immutability is one of the main reasons why deployments are often preferred over direct replica set usage. When it comes to manual updates, replica sets require more hands-on management compared to deployments. If you need to update your application to a new version, you'll need to manually create a new replica set with the updated pod template and carefully manage the transition between old and new replica sets. Some teams struggle with replica set management when they need to perform rolling updates or rollbacks. Without the higher-level abstractions provided by deployments, these operations become complex and error-prone. However, understanding replica sets is still valuable, especially when debugging deployment issues or when you need fine-grained control over pod lifecycle management. They form the foundation for understanding how deployments work under the hood. A practical tip: always use meaningful labels and annotations with your replica sets. This becomes particularly important when you have multiple replica sets running in the same namespace, as it helps with troubleshooting and resource management. Now let's explore deployments, one of the most commonly used Kubernetes objects in production environments. A deployment provides declarative updates for pods and replica sets, offering a higher-level abstraction that makes application management much more straightforward. The primary purpose of a deployment is to manage the desired state of your application. It ensures that a specified number of pod replicas are running at all times, but goes beyond what replica sets offer by providing features like rolling updates and rollbacks. Looking at our example, we're creating a deployment named My App that maintains 3 replicas of a container. This might seem similar to a replica set configuration, but the key difference lies in how deployments handle updates and maintain application state. In production environments, I've found deployments to be invaluable for maintaining application reliability during updates. For example, when you need to update your application to a new version, the deployment controller handles the creation of new pods and the termination of old ones in a controlled manner, ensuring zero downtime updates. A crucial aspect of deployments that's not immediately apparent from the YAML is their ability to maintain deployment history. This history enables you to roll back to previous versions if something goes wrong with an update, a feature that has saved many production deployments from extended downtime. Let's examine the YAML configuration for a Kubernetes deployment in detail. This specification demonstrates the key components needed to deploy and manage your application effectively. The API version apps/v1 indicates that we're using the apps API group, which is the same as replica sets. This is because deployments, like replica sets, are part of the core application management functionality in Kubernetes. In the metadata section, we name our deployment my app. While this example shows a simple name, in production you might want to add labels and annotations for better organization and automation. For example, you might include labels for environment, team ownership, or cost center allocation. The spec section defines the desired state of our application. The replicas field specifies that we want 3 instances of our application running. The selector.match labels field defines how the deployment identifies which pods it should manage. This must match the labels in the pod template. Looking at the pod template, you'll notice it's similar to what we saw in replica sets. However, when used in a deployment, this template can be updated, triggering the deployment controller to perform a rolling update of your application. I recommend always setting resource requests and limits in your pod template, even though they're not shown in this basic example. This helps ensure proper scheduling and prevents resource contention issues. Let's analyze each component of the deployment specification in detail. Understanding these elements is crucial for effectively managing your applications in Kubernetes. The API version and kind fields specify that we're creating a deployment object using the app/v1 API. This is the stable version of the deployments API, used in production environments across the globe. The metadata section contains essential information about your deployment. While our example shows just the name, in production you'll often include additional metadata like labels for environment classification, annotations for deployment tracking, and perhaps even references to monitoring systems. The spec section is where the real power of deployments becomes apparent. The replicas field specifies how many identical pods should be maintained. In production environments, this number is often determined by factors like expected load, resource availability, and high availability requirements. The selector field is crucial. It defines how the deployment identifies which pods it should manage. Label selection errors are a common source of deployment issues. Always ensure your selector matches the labels in your pod template exactly. The template section defines the pod configuration that will be used to create new pods. While our example shows a basic container configuration, in production you'll want to add resource limits, health checks, volume mounts, and possibly init containers or sidecars. Let's explore the key differences between replica sets and deployments, as understanding these distinctions is crucial for choosing the right tool for your use case. Replica sets, as we discussed earlier, manage pods directly and focus on maintaining a desired number of replicas. They're excellent at ensuring basic scaling and high availability, but they lack sophisticated update mechanisms. Deployments, on the other hand, are a higher-level abstraction built on top of replica sets. They manage one or more replica sets to provide advanced features like rolling updates and rollbacks. This is particularly valuable in production environments where zero downtime updates are crucial. Some teams initially start with replica sets and then move to deployments as their applications mature. The main driving factor is usually the need for more sophisticated deployment strategies and the ability to roll back changes quickly if something goes wrong. The rollback capability of deployments is particularly valuable. When working with deployments, you also get the benefit of deployment history and revision tracking. This makes it easier to audit changes and understand when and why certain updates were made to your application. Now let's explore Kubernetes services, a crucial abstraction that enables network access to a dynamic set of pods. Services are essential for building reliable, scalable applications in Kubernetes. The primary purpose of a service is to provide a stable endpoint for accessing your application, regardless of the actual pods that are running at any given time. This is particularly important because pods are ephemeral. They can be created, destroyed, or rescheduled based on various factors. In our example, we're creating a service named MyService that forwards traffic to pods labeled with app, my app. The service exposes port 80 and forwards traffic to port 8080 on the target pods. This port mapping capability is particularly useful when your application needs to expose a different port externally than it uses internally. Services are absolutely critical for building reliable microservices architectures. They provide the necessary abstraction layer that allows your applications to communicate with each other without needing to know the exact location or number of pods providing each service. One important aspect to note is the different types of services available in Kubernetes. While our example uses cluster IP, which provides internal-only access within the cluster, you can also use node port for testing or load balancer for production external access. Let's examine the YAML configuration for a Kubernetes service in detail. This specification shows how to define a service that will provide stable network access to your application pods. Starting with API version v1, we're using the core API group, as services are one of the fundamental Kubernetes resources. The kind field specifies that we're creating a service object. In the metadata section, we name our service MyService. While this example is simple, in production you might add labels for organization and annotations for things like external load balancer configuration or SSL certificate management. The spec section defines how the service should operate. The selector field is crucial. It determines which pods will receive traffic from this service. In our example, pods with the label app, my app will be selected. Looking at the port's configuration, we're defining a TCP port mapping. The service exposes port 80 externally and forwards traffic to port 8080 on the target pods. This port mapping feature is particularly useful when your application needs to maintain separate internal and external port numbers. The type field is set to cluster IP, which means this service will only be accessible within the Kubernetes cluster. This is the default and most common type of service, particularly useful for internal microservices communication. Let's dive deeper into each component of the service specification and understand its significance in a production environment. The API version and kind fields indicate we're working with a core Kubernetes service object. Services were one of the earliest Kubernetes concepts and remain fundamentally important to this day. The metadata section, while basic in our example, can be extended with labels and annotations. In production, you might use annotations to configure load balancer parameters, SSL termination, or session affinity settings. The spec section contains the core service configuration. The selector is particularly important. It uses labels to dynamically discover pods. This label-based selection is what makes services so powerful, as they can automatically adapt to pod scaling, failures, and replacements. The port section deserves special attention. The protocol field specifies TCP, but UDP is also supported. The port field defines what port the service exposes to the cluster, while target port specifies where the traffic should be sent on the target pods. One common gotcha with services is ensuring that the target port matches the actual port your application is listening on in the container. There can be many cases where services appear to be working, but traffic isn't reaching the applications due to port mismatches. The type field being set to cluster IP means this service creates a virtual IP that's only accessible within the cluster. This is perfect for internal microservices, but if you need external access, you might consider using node port or load balancer types instead. Let's explore config maps, a powerful Kubernetes object that helps manage application configuration separately from application code. This separation of configuration from code is a key principle in cloud-native applications. Config maps are designed to store non-sensitive configuration data in key-value pairs. In our example, we're storing a database URL and an API key, though in practice, sensitive data like API keys should be stored in secrets instead. The primary purpose of config maps is to make applications more portable and maintainable. Rather than hard-coding configuration values in your application or container image, you can externalize them in config maps and inject them into your containers at runtime. Config maps are instrumental in managing different configurations across multiple environments. For example, you might have different database URLs for development, staging, and production environments, all managed through different config maps. One important consideration when working with config maps is that they're not automatically updated in your pods when you modify the config map. You'll need to restart your pods or use something like a configuration reloader if you want to pick up config map changes dynamically. Let's examine the YAML configuration for a config map in detail. This specification shows how to store configuration data that can be consumed by your applications. The API version is v1, indicating that config maps are part of the core Kubernetes API. Like services, config maps have been a fundamental part of Kubernetes since the early days. In the metadata section, we name our config map myconfigmap. While our example is simple, in production you might add labels to indicate which application or environment this config map belongs to. The data section is where we define our key value pairs. Each key becomes a potential environment variable name or file name when mounted into a container. The values can be simple strings, as shown here, or even entire configuration files. One common pattern is to use config maps to store application configuration files. For example, you might store an nginx.conference or application.properties file as a value in your config map. A practical tip: when dealing with larger configuration files, you can use the vertical bar character in YAML to maintain proper formatting. For example, data, nginx.conference, server, listen, 80. This makes it much easier to maintain complex configuration files within your config maps. Let's dive deeper into the components of a config map and understand how they work in practice. The API version and kind fields specify that we're creating a config map object using the core v1 API. This is one of the most stable APIs in Kubernetes, so you can rely on its behavior being consistent across versions. The metadata section, while minimal in our example, can include labels and annotations for better organization and automation. In production environments, you might use labels to indicate the application, environment, or team that owns the config map. The data section is where the actual configuration lives. Each key value pair in this section becomes available to your pods either as environment variables or as files in a volume mount. The choice between these two methods depends on your application's needs. There are several best practices to consider when working with config maps. 1. Use meaningful key names that clearly indicate their purpose. 2. Consider using prefixes to avoid naming conflicts. Document the expected format and values for each configuration item. 4. Maintain separate config maps for different aspects of your application. Remember that config maps have a size limit, 1 megabyte by default, so they're not suitable for very large configuration files. For such cases, you might need to consider alternative solutions like mounted volumes or initialization containers. Now let's explore Kubernetes secrets, which are specifically designed for storing and managing sensitive information such as passwords, oath tokens, SSH keys, and other confidential data. The key difference between secrets and config maps is that secrets are specifically intended for confidential data. While both can store key value pairs, Secrets are handled more securely by Kubernetes. For example, secrets are only distributed to nodes that have pods requiring them, and they're typically stored in encrypted form. In our example, we're creating a secret named MySecret with username and password values. Notice that the values must be base 64 encoded. This encoding is not for security, it's easily reversible, but rather to allow storage of binary data and prevent issues with special characters. Proper secret management is crucial for application security. However, it's important to understand that Kubernetes secrets are not encrypted by default. They're only base 64 encoded. To achieve true security, you should enable encryption at rest for your etcd database. 2. Use Rebake to control access to secrets. 3. Consider using external secret management solutions like HashiCorp Vault or AWS Secrets Manager. One common mistake is to commit secrets to version control. Always ensure your secrets are managed separately from your application code and infrastructure configuration. Let's examine the YAML configuration for a Kubernetes secret in detail. This specification shows how to properly define sensitive data in your cluster. The API version is v1, as secrets are part of the core Kubernetes API. The kind field specifies that we're creating a secret object. In the metadata section, we name our secret MySecret. The type field is set to opaque, which is the default secret type used for arbitrary user-defined data. Other types include Kubernetes.io/service, account token, Kubernetes.io/docker, CFG, and Kubernetes.io/TLS for specific use cases. The data section contains our key value pairs, with values base 64 encoded. In our example, we're storing a username and password. Remember that while the values appear encrypted, base 64 encoding is not encryption. It's merely an encoding scheme to allow storage of binary data. Instead of manually base 64 encoding your values, you can use the string data field. String data, username, actual username, password, actual password. This allows you to write the actual values directly, and Kubernetes will handle the base 64 encoding for you. This makes the YAML more readable and less error-prone. Let's explore how to effectively use secrets in your pod configurations. This is a crucial aspect of securing your applications in Kubernetes. In the example shown, we're mounting secret values as environment variables in our pods container. The env section defines environment variables that reference specific keys from our secret using the secret key ref field. The configuration demonstrates two environment variables, db_username and db_password, both pulled from a secret named MySecret. This is a common pattern for database credentials, but it can be used for any sensitive configuration your application needs. There are several important considerations when using secrets. 1. Environment variables are visible to anyone who can exec into the pod. 2. They appear in container runtime logs. 3. Child processes inherit environment variables. For more sensitive data, consider using volume mounts instead of environment variables. With volume mounts, the secret values appear as files in your container's file system, which can be more secure and easier to manage for some applications. Another best practice is to ensure your application handles secret rotation gracefully. Consider implementing periodic pod restarts or using tools that can detect and react to secret changes. Let's examine how to manage secrets in a GitOps workflow, particularly when using GitHub Actions for deployment. The YAML configuration shown demonstrates a GitHub Actions workflow for deploying to Kubernetes while securely handling sensitive information. This is a crucial aspect of maintaining security in your DevOps pipeline. The workflow uses GitHub's secret management system to store sensitive values like kubeconfig, db_username, and db_password. These secrets are then accessed securely during the deployment process using the secrets context. A key part of this approach is the use of environment variables and sed commands to replace placeholders in your Kubernetes manifests. This allows you to keep your base configurations in version control without exposing sensitive data. Here are some important considerations. 1. Never store the actual secret values in your Git repository. 2. Use separate secrets for different environments: dev, staging, prod. 3. Implement proper airbag for GitHub Actions workflows. 4. Regularly rotate your secrets and access credentials. 5. Audit your GitHub Actions secrets usage regularly. Remember that while GitHub secrets provide good security, they're still accessible to anyone with workflow modification permissions. Consider implementing additional approval processes for production deployments. Now let's explore the horizontal pod autoscaler, HPA, a powerful feature in Kubernetes that automatically adjusts the number of pods in a deployment based on observed metrics. The first crucial component for HPA is the metrics server. This component collects resource utilization data from your cluster's nodes and pods. Without the metrics server, HPA won't have the data it needs to make scaling decisions. Resource requests and limits play a vital role in HPA's decision-making process. When you define these in your pod specifications, you're not just setting constraints, you're also providing the baseline metrics that HPA uses to determine when to scale. Proper configuration of resource requests is crucial for effective autoscaling. If your requests are too low, HPA might not scale up when needed. If they're too high, you might waste cluster resources. A common pattern successful is starting with CPU-based autoscaling and then gradually incorporating custom metrics as you better understand your application's scaling characteristics. This allows you to build confidence in your autoscaling configuration before making it more sophisticated. Let's continue our discussion of horizontal pod autoscaler by focusing on its implementation and configuration aspects. When creating or updating a deployment or replica set for autoscaling, it's important to ensure that your pod template includes appropriate resource requests. These requests serve as the baseline for HPA's scaling decisions. The autoscaling behavior can be customized by defining your own HPA object. This gives you fine-grained control over scaling parameters such as minimum and maximum replicas, scaling metrics, and cooldown periods. Here are some crucial considerations. 1. Set appropriate minimum and maximum replica counts based on your application's characteristics. 2. Consider both scale-up and scale-down behaviors. 3. Test your autoscaling configuration under realistic load conditions. 4. Monitor your HPA's decisions to ensure they align with your expectations. One common mistake is not accounting for application startup time when configuring HPA. If your application takes several minutes to start, you might need to adjust your HPA's scaling policies to prevent overwhelming your cluster during rapid scale-up events. Let's examine the YAML configuration for a horizontal pod autoscaler in detail. This specification shows how to define automatic scaling behavior for your applications. We're using API version autoscaling/v2 beta 2, which provides more advanced features compared to the v1 version. The kind field specifies that we're creating an HPA object. The spec section contains several crucial components. Scale target ref identifies the resource to scale, in this case, a deployment. Min replicas and max replicas set the scaling boundaries. Metrics define what we're measuring to make scaling decisions. In our example, we're using CPU utilization as the scaling metric with a target of 50%. This means HPA will try to maintain average CPU utilization across all pods at 50% by scaling up or down within the specified replica limits. CPU-based autoscaling works well for many applications, but there are some important considerations. CPU. utilization isn't always the best metric for scaling decisions. 2. Consider using memory metrics or custom metrics for memory-intensive applications. 3. Be cautious with very low or very high target utilization percentages. 4. Account for your application's scaling characteristics when setting targets. We've covered key Kubernetes objects in this module. Let's review the main concepts. Pods are the smallest deployable units, providing a shared environment for containers. We learned how to define them using Yamame and their configuration options. Replica sets and deployments manage pod lifecycle, enabling scaling and rolling updates. We covered when to use each controller type. Services provide stable networking endpoints for applications, with different types for various use cases. Config maps and secrets handle configuration management and sensitive information, separating config from application code. We explored horizontal pod autoscaler for automatic scaling based on metrics. Practice with these objects in a test cluster to understand how they work together. These fundamentals form the basis for advanced Kubernetes concepts. Common scenarios to consider. Pods, replica sets, and deployments form a hierarchy of management. Services provide stable networking for pods. Evaluate additional security measures beyond basic secrets. Follow best practices for configuration management. Consider application characteristics when setting autoscaling parameters. Take time to understand these building blocks as they're essential for cloud-native development.